Some features add signal, others add noise. Mutual information gives you a fast scikit-learn filter before the model ever trains. This is the setup you'll be able to run after this, which ranks features by mutual information before training. I'm Professor Pi, teaching AI foundations with simple Python. Too many features, slow models, and hide the useful signals. Feature selection is the filter you run before training to drop the noisy columns. Mutual information helps because it measures how much a feature and the label share, even when the relationship isn't linear. That makes it an excellent first-pass filter when you want to speed up training or reduce overfitting on small to medium datasets. Put simply, mutual information answers, how much does knowing one value reduce uncertainty about the other? If the word discount shows up a lot in spam, that feature shares a lot of mutual information with the spam label. It works well for categorical and count data. The downside, you need enough examples to estimate dependence reliably, so tiny samples can be noisy. We'll build a compact, clear example. We'll create a tiny table of 6 observations, compute mutual information per column, pick the top 2 features, and test a logistic regression on that reduced set. The goal is to show the whole flow, step by step, from raw table to a model-ready feature subset. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now let us build that tiny example so the idea lands. This snippet prepares a compact pandas dataset that will anchor later mutual information experiments. The pandas import loads the DataFrame API we need to manipulate small tables without extra tooling. The data variable captures 6 customer-like observations with word counts, link flags, and review ratings chosen to mix strong and weak signals. The target series pairs each row with ham or spam, so scikit-learn algorithms can treat the classification labels consistently across future steps. The printed counts show we have 6 rows split evenly across 2 classes, ensuring upcoming information scores have room to differentiate features. We have raw counts and labels now, but numbers mean nothing until we measure dependency. The next step computes a mutual information score for each column so we can rank them by how predictive they are. This example feeds the dataset into scikit-learn to compute mutual information scores per feature. LabelEncoder from sklearn.preprocessing converts the string target into numeric codes because mutual info classif expects an integer labeled target array. The data frame becomes a numpy array through 2 numpy, so the feature selector receives contiguous numeric inputs. Mutual info classif estimates the dependency between each column and the encoded labels, and random state equals 0 keeps the small noise jitter stable between runs. The printed list reveals how strongly each feature relates to the class labels, giving us an initial hierarchy to build upon. Numbers tell a story, but we need a readable order. The next step wraps those scores with names and sorts them so we can point to the strongest feature immediately. This code ranks the mutual information scores so we can see the standout signal at a glance. A pandas series wraps the raw array and labels it with the original column names, making the numbers easier to read. Sort values orders that series from strongest to weakest dependency, which helps us focus on the most informative dimensions first. Extracting top name and top score separates the leader, so later steps can reference it directly without repeated indexing. The printed message confirms which feature currently carries the most information and quantifies the margin it holds. Seeing which features win is useful, but we often need a fixed size subset to feed a model. The next block shows how to automatically pick the top 2 features. This snippet applies scikit-learn SelectKBest to keep only the two most informative fields. SelectKBest couples mutual info classif with k equals 2, instructing scikit-learn to choose the top two columns ranked by mutual information. Calling fit learns those scores using the same x and y arrays, and get support converts the winning mask into a convenient Boolean selector. We retain the reduced data frame for interpretation and keep the NumPy array x selected so model training can proceed without further slicing. Increasing k would preserve more columns, but risks letting noisy inputs slip through, while decreasing it would funnel the model onto a single signal. The printed column list shows exactly which features survived the filter, confirming the selection step worked. With the reduced feature set in hand, we need to know whether it actually helps a classifier. The final snippet runs a quick evaluation to quantify predictive power. This example trains a logistic regression baseline on the filtered features to quantify their predictive power. Logistic regression from scikit-learn.linear model becomes our lightweight classifier, and setting random state along with the liblinear solver stabilizes optimization on tiny datasets. Cross-val score evaluates the model with 3 stratified folds, giving a reliable snapshot of performance without needing a separate holdout set. Averaging the fold results into mean score produces a single figure that we can track as we explore alternative feature sets. Raising CV would introduce more folds, but with such few rows, the variance would spike because each split would hold too little data. The printed accuracy expresses how well the mutual information selected columns currently support the classifier. In a real project, this toy flow maps directly. Swap the 6 rows for thousands. Keep the same mutual information filter, and you get a lightweight way to remove irrelevant columns before heavy training or expensive embeddings. On larger data, the scores will stabilize, and the selection will cut CPU and memory for downstream models. Recap: mutual information feature selection measures shared information between features and the label, so it finds both linear and nonlinear signals. Use it as a fast, model-agnostic filter when you want to reduce dimensionality or speed up training. Caveat: it needs enough examples for stable estimates, so be cautious on very small datasets. Next step: tune the k parameter in SelectKBest and compare cross-validation score as you increase k to see the trade-off between signal retention and added noise. If AI foundations in Python help, subscribe and watch the AI Foundations videos.